Good day to all of you. This is the second lecture in the subject of electrostatics. Let me recall what we did in the last lecture. I started with some demonstration experiments where I showed that if you take two pieces of straw and rub them with wool, then the two straws repel each other. The repelling force comes even when I put one of the straws close to the other straw, do not even touch it. So, one straw is pushing the other straw with certain force. We also saw that if I take a glass rod which is rubbed with silk close to the plastic straw, then the glass rod attracts the plastic straw. The plastic straw which was charged gets repelled by another plastic straw, but the glass rod attracts the plastic straw. So, there seem to be two kinds of forces, one which is a repulsive force and one which is a attractive force. To explain this, we introduce the concept of charge. As I mentioned last time, charge is an attribute of a particle much like mass. So, if you have different particles, just like they have different masses, they can have different charges. And we explain the experiments of repulsion and attraction by saying that there are two types of charges. There are two types of charges, one is called positive, the other is called negative. And the positive charge repels the positive charge, negative charge repels the negative charge, while positive charge attracts the negative charge and negative charge attracts the positive charge. So, with these two charges, we are able to explain the phenomenon of repulsion and attraction that was seen in those experiments. We also discussed different properties of charges. For example, first one is conservation of charge. If you take an isolated system with certain charges, then the total charge in that isolated system does not change. By isolated, I mean you do not allow any charge to come from outside into the system or any charge to leave the system. This says that the total charge within the isolated system is constant. It does not imply that the number of negative charges and number of positive charges is constant. As I mentioned in the last lecture, sometimes it is possible to generate new charges within the isolated system, but whenever you generate a negative charge, you will also in parallel generate a positive charge. So, the total charge of the system will remain constant, and this is a property of conservation of charge. We also saw that charge is quantized. That is, the charge comes in quanta of approximately a charge which is 1.6 10 to the minus 19 Coulomb. So, all charges that you will ever find, positive or negative, will all be integral multiples of this number. So, you can have any integral multiple of this quantum of charge. You cannot have a charge which is say 2.9 times this number. So, this quantization of charge is another very important property, and third thing is additivity of charges. So, if you have n 1 positive charges and n 2 negative charges, then the total charge in the system will be n 1 minus n 2 into E. So, you just add charges just like you add numbers, keeping the sign of the charge in mind. So, when you have equal number of negative and positive charges, the net charge becomes 0. We then introduce the concept of conductors and insulators. Conductors are those substances in which there are free electrons that can move within the material. So, if you push some charges on these conductors, they will distribute themselves all around the surface of the conductor. Insulators are materials in which this free movement of charges does not take place. So, if you charge an insulator at some point, the charge sticks to that point and is unable to move around the insulator. I also talked about semiconductors, which have conductivity between conductors and insulators, and semiconductors form a very important part of the electronics revolution. We then introduced Coulomb's law. As the force between two charges. So, let me recall, if I have a charge q 1 and another charge q 2, if this is my origin, I have one vector here which is called r 1 vector, another vector here which is called r 2 vector here. This vector is r 2 1 vector, and r 2 1 vector is equal to r 2 minus r 1. So, we said that according to Coulomb's law, the force on charge 2 because of charge 1 is 1 by 4 pi epsilon 0 q 1 q 2 by r 2 1 square into r 2 1 unit vector. So, the force is proportional to the product of the two charges, inversely proportional to the square of the distance between the two charges, and is along the direction along a line connecting the two charges. As I mentioned, this formula is valid whether the charges are positive or negative. So, if both charges are positive, then the direction of the force F 2 1 is the same as the direction of r 2 1 unit vector. R 2 1 vector goes from q 1 to q 2, and so if the charges are both positive, the force on q 2 is in this direction, which is repulsive. So, this charge is repelling this charge. Similarly, if q 1 was negative and q 2 was also negative, then this force again becomes positive, product of two negative numbers here. So, the force has the same direction as the direction of r 2 1 unit vector. So, the force on q 2 because of q 1 is again in this direction, which is again repulsive. If the sign of q 1 and q 2 were opposite, if one was positive, the other was negative, then the direction of the force F 2 1 is opposite to the direction of the unit vector r 2 1, and the force becomes attractive. So, if for example, this is positive and this is negative, then the force acting on this charge is towards q 1, which is attractive. Now, please remember that this force on 1 because of 2 is equal to 1 by 4 pi epsilon 0 q 1 q 2 by r 1 2 square into r 1 2 unit vector. Now, what is r 1 2 unit vector? R 1 2 vector is equal to r 1 minus r 2 vector, which is actually minus of r 2 minus r 1 vector, which is equal to minus r21 vector. So, r12 is oppositely directed. So, if this is q1, this is q2, this is r1, this is r2, this is r12. So, the force as you can see here F12 becomes 1 by 4 pi epsilon 0 q1 q2 by r. Now, because r12 vector is minus of r21 vector, the magnitude of r12 vector is equal to magnitude of r21 vector. So, I can write here r21 square instead of r12, and r12 unit vector is minus r21 unit vector. So, I put a minus sign here and I put r21. So, as you can see here, the force on charge 1 because of 2 is exactly equal and opposite to the force of q1 and q2. So, if q1 repels q2 with a certain force, q2 repels q1 with the same force in the reverse direction, and this is nothing but a statement, is a confirmation of Newton's third law. This force, as you can see here, is very similar to the law of gravitation, except that in gravitational there is only attractive force because there is only one kind of mass. Okay. Now, we go to let me try to recall what we did in the experiment. Remember, I had two straws in which we had rubbed the two straws with wool, and we found that it was repelling each other. So, what is actually happening is when you rub straw on another surface, the straw picks up some electrons from the wool and becomes charged, excess charge of negative, and wool loses the charge. So, please remember, there is no generation of new charge. All that has happened is some charge from the wool has moved to the plastic straw. Similarly, when I rubbed the other straw, some charge moved from wool to the other straw, and this was the same charge as moved to the first straw. So, the two straws after rubbing have identical charges, similar charges, both are negative, and hence they repelled each other, as we saw in the experiment. On the other hand, when I rubbed glass with silk, it so happens that glass loses electrons into the silk. So, if you lose electrons from glass, glass will have excess positive charge compared to negative charge, and it gets positively charged. So, when you bring glass close to the plastic straw, the positive charge in the glass attracts the negative charge in the straw, and as we saw in the experiment, they stick to each other. So, this is essentially the explanation of what we observed the other day in the demonstration. So, now let us start with some concepts that, please remember, I told you that the unit of charge is Coulomb. But 1 Coulomb is a huge charge, because you remember one electron charge in magnitude is 1.6 10 to the minus 19 coulombs. So, in 1 Coulomb, the number of electrons is 1 by 1.6 10 to the minus 19, which is approximately 6 into 10 to the power 18. So, 6 times 10 to the power 18 electrons are there in 1 Coulomb, and that is a very, very huge charge. So, we normally in problems we deal with much smaller charges, things like, for example, 1 microcoulomb, written like this. This is 1 microcoulomb, this is 10 raised to minus 6 coulomb. 1 nanocoulomb which is 10 to the minus 9 Coulomb. I thought it may be interesting for you to have a knowledge of the following quantities which represent, for example, there is milli, which is m, which corresponds to 10 to the minus 3 millimeter, 10 to the minus 3 meters, milligram is 10 to the minus 3 grams. Then you have micro, which is written as mu, and that is 10 to the minus 6. Then you have nano, which is written as small n, which is 10 to the minus 9. Then you have pico, which is written as p, which is actually 10 to the minus 12. So, you see we are decreasing by a factor of 1000 every time. Then we have femto, written as f, this is 10 to the minus 15. Then we have atto, 10 to the minus 18. So, 1 atto Coulomb would mean 10 to the minus 18 coulombs. Then you have zepto, which is small z, is 10 to the minus 21, and yocto, small y, which is 10 to the minus 24. So, these are all quantities which can be used. Normally, we tend to use milli, micro, nano, pico, femto, but today these days there are also physical quantities at the scale of atto and zepto. So, I thought it may be interesting for you to learn that what are these descriptions of these kinds of numbers. On the other side, we also have kilo, which is k, 10 to the power 3. Then you have mega, which is capital M, 10 to the power 6. Then you have giga, g, which is 10 to the power 9. Then you have tera, capital T, which is 10 to the power 12. Then you have peta, which is 10 to the power 15. Then you have exa, E, which is 10 to the power 18. Then you have zeta, capital Z, which is 10 to the power 21, and finally iota, capital Y, which is 10 to the power 24. I thought I will just mention about this, because many times in physics and engineering you will tend to use quantities which are quite small in numbers or large in numbers, and then you will have to use some of these powers to explain those quantities. Okay. So, now I would like to introduce another very important concept in electrostatics, and that is the principle of superposition. So, earlier what we have discussed is the force acting on a charge because of the presence of another charge. It is not necessary I just have 2 charges, there may be many charges. So, what happens if I have instead of 2 charges 3 charges? So, let me look at the following problem. So, I have a charge q2, I have a charge q1, and I have a charge q3. So, this is my some origin here, this is my origin here O, this is R2 vector, this is R1 vector, and this is R3 vector. So, you have these vectors R12 vector here, and here you have R13 vector. So, the question is the following, these are the 3 charges here, 3 point charges. The question is, what is the force on q1 in the presence of both charges q2 and q3? So, what I do is the following, I keep Q1 here and Q2 here and move Q3 to infinity, very far away. So, you know that if I move Q3 to a very large distance, it will hardly have any force on Q1, because remember the force on Q1 because of Q3 will decrease as 1 by this distance square. So, if this distance becomes very, very large, then the force of Q3 on Q1 will almost become 0. So, then I will have a force on Q1 because only because of Q2. So, let me call this F12. So, F12 is the force on the charge Q1 because of charge Q2 only in the absence of any other charge. Then what I do is I bring back Q3, put it back in this position, move Q2 to infinity, very large distances. And again, if Q2 moves to very large distances, because the force of this charge Q2 on Q1 is inversely dependent on square of this distance, as this distance keeps on increasing, the force of Q2 on Q1 will become almost 0. So, then what I will have is Q1 will see a force only because of Q3. So, let me call that as F13. So, F12 is the force on Q1 because of Q2 in the absence of Q3. F13 is the force on Q1 because of Q3 in the absence of Q2. Now, I put both the charges in this position and I want to calculate what is the force on Q1. So, what is found is the force on Q1, which I call F1, is actually F12 plus F13. That means, this force on this charge Q1 is the sum of the force on the charge Q1 because of Q2 in the absence of Q3 and the force on Q1 because of Q3 in the absence of Q2. So, the force on Q1 because of Q2, which is this quantity, does not change even if Q3 is sitting here, that is remains as F12. Similarly, the force applied by Q3 on Q1 is the same as if Q2 did not exist. The total force on Q1 is the vector sum of the force of Q2 on Q1 and the force of Q3 on Q1. This is called the principle of superposition. That means, to calculate the total force on a charge, I add up the forces of each individual charge on this charge vectorially, and that gives me the total force. Now, this is a very, very significant result. That cannot be predicted by any logical argument. It just so happens that electrostatics follows this principle of superposition. So, the force of interaction between any two charges is not affected by the presence of any other charge in the system, and that is very, very important for our understanding. Now, I must mention that there may be domains of applications where this principle may fail. This may happen in extremely small distances or in the presence of very, very intense forces. But in all our discussion, we will use the principle of superposition, and so no matter how many charges are there in the system, the force on any charge will be simply the vector sum of the force by each charge on this particular charge, which can be obtained from Coulomb's law. So, in this problem, in this example here, as we see, the total force on Q1 is the force on Q1 because of Q2 plus the force on Q1 because of Q3. So, I can write the following expression: F1 is equal to 1 upon 4 pi epsilon 0 Q1 Q2 by R12 square R12 cap plus 1 by 4 pi epsilon 0 Q1 Q3 by R13 square R13 cap. So, this is F12 and this is F13. So, this force is the force on Q2 because of on Q1 because of Q2 irrespective of whether Q3 was there or not. Similarly, this is the force on Q1 because of Q3 independent of the presence of Q2. So, this is the principle of superposition. So, if you have a large number of charges, large number of point charges, I can write the total force on a charge Q1 as sigma j is equal to 2 to n. There are suppose n charges, 1 upon 4 pi epsilon 0 Q1 Qj divided by R1 j square R1 j cap. Note that this summation does not include the charge on which I am calculating the force. In this figure, Q1 is not applying any force on itself. The force on Q1 is determined only by the charges Q2 and Q3. So, similarly, here in the summation, the force on the charge Q1 depends on all other charges corresponding to Q2, Q3 etcetera up to Qn, and this is the corresponding distance of the jth charge from Q1, and this is the unit vector along the line joining the jth charge to Q1. So, this helps me to calculate the total force on any charge. So, for example, if I wish to calculate the force on charge Q2 in this system, I would have to write like this: F2 vector will be sigma j is equal to 1 and j is equal to 2 to n 3 to n 1 by 4 pi epsilon 0 Q2 Qj by R2 j square R2 j unit vector. So, this does not include charge Q2, it includes charge 1 Q1 and Q3 to Qn, all the other charges except the charge Q2 on which I am trying to calculate the force. Please remember that force is a vector quantity, and so I must add all these forces vectorially. Now, to make things clear, I want to take 1 or 2 examples to calculate the total force and to understand how does one estimate the force on one particular charge in the presence of other charges. So, let me look at example 1. So, I am given the following problem. I have a charge which I call Q1 here, another charge Q2 and a third charge Q3. Now, as an example, I am taking all the 3 charges along one line. Let me write this as minus 20 nanocoulomb. So, this is actually minus 20 into, so this is minus 20 10 to the power minus 9 coulomb. This is for example, let me take plus 5 nanocoulomb. This is 5 into 10 to the power minus 9 coulomb, and let me assume this is plus 8 nanocoulomb. So, this is 8 into 10 to the power minus 9 coulomb, and I am given that this distance is 1 meter and this distance is half a meter. So, I have 3 charges kept along a line Q1, Q2, Q3. Q1 is minus 20 nanocoulomb, Q2 is plus 5 nanocoulomb, Q3 is plus 8 nanocoulomb. So, I want to find out what is the force, what is the electrostatic force on Q3. So, I want to find out what is the force because of these 2 charges on Q3. Now, please note that all the 3 charges in my example are along one line, So, the force of this charge on this charge does not depend on the existence of this charge at all, it is on the way, but this force of this charge on this charge, it depends only on the separation between these two charges and the two charges between. Similarly, the force of this charge on this charge is independent of the presence of the charge q1 according to our principle of superposition. Now, in physics we should take the origin and axes to help us solve the problem easily. I could in general take an origin at any place, axis in any direction, but it will help me to take the origin here. So, I take a coordinate system like this. So, this is y axis and let me take x axis like this. So, let me redraw the figure here. So, I have q1, q2 and a third q3. So, this is y axis, x axis. Now, this will help me to solve the problem a little more easily. As I mentioned, it is not necessary, I could have taken the origin at any point. So, the force on q3 is actually equal to F31 plus F32. The force on q3 because of q1 plus force on q3 because of q2. Now, what is F31? 1 by, so that is the force on q3 because of q1, 4 pi epsilon 0 q1 q3 by r31 square r31 unit vector. Now, what is r31? So, the distance is given to me are 1 meter and this is 0.5 meters. So, r31 magnitude is equal to 1.5 meters and r31 unit vector is nothing but unit vector along the x direction, because this line is along the x direction and the line joining q1 to q3 is along the x axis. So, r31 becomes simply 1.5 meters. So, actually r31 vector is 1.5 x cap. Similarly, what is F32? F32 is equal to 1 by 4 pi epsilon 0 q2 q3 by r32 square r32 unit vector. R32 vector is actually R3 vector minus R2 vector, which is equal to 0.5 into x cap, because again if you can see here the line joining 2 to 3 is along the x axis. So, R32 is also the same as, it has the same unit vector direction x cap and has a magnitude. So, magnitude of R32 vector is actually 0.5 meters, which is the distance from 2 to 3. So, I have got the total force on q3 is the sum of the force on 3 because of 1 plus the force on q3 because of charge 2, and these are the two numbers. So, I can actually calculate immediately the two forces. So, F31 is equal to, so I need to calculate this. So, let me substitute this number, 1 by 4 pi epsilon 0 is 9 into 10 to the power 9 into q1 was given as minus 20 nanocoulomb, q3 is 8 nanocoulomb divided by the distance square, which is 1.5 square, which is 2.25, and this comes out to be minus 6.4 into R31 unit vector. So, 6.4 into 10 to the minus 7 x cap Newton, that is a force, minus 6.4 10 to the minus 7 x cap. What does the minus sign indicate? The minus sign, minus x cap, it is the vector direction. So, that indicates that the force is in this direction, and you can appreciate that because this is negatively charged, this is positively charged. So, it is a force of attraction. So, this charge which is negative is attracting this charge which is positive, and so the force on q 3 because of q 1 is along minus x cap direction. What about F 32? Let us calculate that. F 32 is equal to 1 by 4 pi epsilon 0 q 2 q 3 by r 32 square r 32 unit vector, which is equal to 9 into 10 to the power 9. Q 2 is 5 nanocoulomb and Q 3 is 8 nanocoulomb divided by 0.5 square, which is 0.25, and this comes out to be 1.44 into 10 to the minus 6 x cap Newton. This is a positive force. This force is along x cap direction, which means that the charge q 2 is actually repelling q 3, because the force on q 3 because of q 2 is along the plus x cap direction. The force on q 3 because of q 1 is along minus x cap direction. So, that is a force of attraction. So, q 1 attracts q 3 irrespective of the presence of q 2. The force of q 1 on q 3 is exactly given by the Coulomb's law without any worries about the presence or absence of q 2. Similarly, the force on q 3 because of q 2 is again obtained by Coulomb's law, and it happens to be repulsive because they have the same sign charges. So, I can calculate the total force on q 3, which is equal to minus 6.4 10 to the minus 7 x cap plus 1.44 into 10 to the minus 6 x cap, which happens to be equal to 8 into 10 to the minus 7 x cap. So many newtons. So, what does it imply? This force, this charge which is sitting here will feel a force which is in the plus x cap direction, because the force has a vector direction along x cap. So, this force, this charge is trying to attract this charge is trying to repel it, and it so happens in this calculation that because this is closer to these two charges, or closer, much closer than these two, this repulsive force is stronger than the attractive force of this, and the net force on this charge becomes repulsive rather than attractive. So, if I have this problem here, if I fix these two charges, this charge will be trying to be pushed out away from this point along this line. Now, one obvious question arises: is there any point in this plane at which point there is no force on the charge q 3? Can I have a situation, can I have a point on this plane where if I place q 3, it does not suffer any force? Now, the first thing you can notice is, because force is a vector quantity, if you take the charge q 3 on at any point other than the x axis. So, let me just put q 1 here, q 2 and q 3. So, if I move q 3 from here to here, this force will be like this, because this is attractive. This is minus 20 nanocoulomb, this is plus 5 nanocoulomb, and this force will be like this, repulsive. So, obviously, these two forces cannot cancel each other even if they have similar magnitudes. So, if you take any point anywhere on this plane except along the x axis, you will find that these two vectors cannot cancel each other at all. So, we expect the point, if at all, to lie on this line, on this x axis of this problem. So, to solve the problem, let me assume that I have q 1 here, q 2 here, and some point here which where I put q 3, and let me assume this distance is x. This is 1 meter. So, I assume the charge q 3 to be present at some point x, such that the net force becomes 0. So, two things I must satisfy. One is that the force directions must be equal, the force by this charge and by the force by this charge on the charge q 3 must be equal and opposite to each other. So, first thing is, by moving it on the x axis, I have ensured that the force of Q1 on Q3 and Q2 on Q3 are along the same line. I still do not know whether they will be in the same direction or opposite directions. So, first thing is by ensuring that my charge is on this plane, on this line of x axis, the force of repulsion of Q1 on Q3 and the force of attraction of Q2 on Q3 will be along the same line. And not only they must be opposite in direction, but also equal in magnitude. So, let me try to find out where are the points on the x axis where the forces between Q1 and Q3 and Q2 and Q3 become equal in magnitude. So, I want to look at a point where F13 magnitude is equal to magnitude F23. So, what is the force because of 1 on 3? So, this distance is x. So, I will have F13 magnitude is equal to 1 by 4 pi epsilon 0 Q1 Q3 by x square. So, there is no x cap, this is the magnitude. Similarly, F23 magnitude is equal to 1 by 4 pi epsilon 0 Q2 Q3. So, these are all magnitude, I am putting magnitude here, divided by now this distance. So, that is x minus 1 whole square. So, magnitude of this is the magnitude of force of Q1 on Q3, this is the magnitude of force of Q2 on Q3, and let me put them equal to each other to find out the value of x. So, I have 1 by 4 pi epsilon 0 Q1 Q3 by x square is equal to 1 upon 4 pi epsilon 0 Q2 Q3 upon x minus 1 whole square. So, I cancel this off, I cancel off Q3. So, I get x minus 1 square by x square is equal to mod Q2 by mod Q1, and this Q2 is 5 nanocoulomb and magnitude of Q1 is 20 nanocoulomb. So, that is 1 by 4. So, this implies x minus 1 by x is equal to plus minus half. So, this there are two solutions. One is if x minus 1 by x is equal to plus half, this implies if I cross multiply 2 times x minus 1 is equal to x, which implies x is equal to 2. So, this is one point where the forces of Q1 and Q2 on the Q3 charge are equal. The second solution, if I look, x minus 1 by x is equal to minus half, this implies 2 times x minus 1 is equal to minus x, which implies x is equal to 2 by 3. 2x plus x is equal to 2. So, that is x is equal to 2 by 3. Now, if I look at these 2 points, the 2 solutions, they seem to be like this. So, I have Q1 which is minus 20 nanocoulomb, Q3 Q2 which is plus 5 nanocoulomb, and there is Q3 here which is plus 8 nanocoulomb, and this is my distance x. So, there are 2 solutions. The first solution is to the right of Q2, because x is 2 meters and this distance I know is 1 meter. So, this first solution is 2 meters, that means 1 meter from Q2. If I keep the charge, the net force will become 0. The magnitude of the force because of Q1 on Q3 and magnitude of the force of Q2 on Q3 become equal. Now, this point is such that, remember, at this point Q1 has a force like this and Q2 has a force like this, because this is Q1 has a attractive force and Q2 has a repulsive force. These 2 forces are opposite in direction, equal in magnitude. So, this point x is equal to 2 meters is a point where the force on Q3 becomes 0, because the force of Q1 on Q3 is equal to force on Q2 and Q3, and the force because of Q1 on Q3 and because of Q2 on Q3 are in opposite directions. So, Q1 tries to attract Q3, Q2 tries to repel Q3, but with the same magnitude along opposite directions. So, the result is Q3 has no force acting on it. Now, I would like you to think about the second solution, which is between Q1 and Q2, because that solution is x is equal to 2 by 3 meters. At this point, what is the solution which I have got in my problem? So, please give a thought and find out what is happening at this point where the two forces become equal. I will leave it as a small exercise to you, just give some thought and try to find out what is the significance of this point. Now, I would like to take another example, which is so this example was three charges on a same line. Now, I want to take another example where the charges are not along the same line, but in a plane. So, let me take as an example. So, this is Q1, Q2 and Q3. So, let me assume 10 nanocoulomb here, plus 10 nanocoulomb, plus 10 nanocoulomb and plus 5 nanocoulomb. And just to give you some numbers, let me take this as 20 centimeter, this is 10 centimeter, and this is divides equally. So, this is 10 and this is 10. So, three charges are kept. This is one charge here, there is another charge here and a third charge. So, I want to find out what is the force on Q3. So, now these three charges are not along the same line, they are at three different points on this plane. So, again just like I did in the earlier example, it is good for me to choose an appropriate coordinate system. So, I will choose the following coordinate system. So, these are my three charges, one charge here, another charge here, another charge here. So, let me take this to be y axis and this to be x axis. So, this is Q1, Q2 and Q3. So, this is origin. So, this is R1, this is R2 and this is R3. So, what are these quantities? R1 vector is equal to, so please remember this is given as 10 centimeters. So, that is 0.1 meters into y cap. This is R1 vector has a magnitude of 0.1 meters and is along the y direction. R2 vector has a magnitude 0.1 again and is along the minus y direction. So, there is a minus sign here and y cap, and R3 vector is actually this from here to here. It has the same magnitude of 0.1 meters and is along x cap. So, R1 vector is 0.1 y cap, 0.1 is this distance into y cap is along y direction. R2 vector is minus 0.1 into y cap, because this distance is 0.1 meters and in the minus y direction. R3 vector is plus 0.1 into x cap. So, R31 is equal to R3 minus R1, which is equal to 0.1 into x cap minus y cap. X cap is unit vector along the x direction, y cap is unit vector along the y direction. Similarly, R32 will be R3 minus R2, which is equal to 0.1 into x cap plus y cap. So, these are the two vectors, because to calculate the force on Q3, I have to calculate the force on Q3 because of Q1 by Coulomb's law, plus the force on Q3 by Q2 from Coulomb's law, and add the two vector forces. So, I would need r 3 1 unit vector and r 3 2 unit vector. So, this is equal to r 3 1 vector by magnitude of r 3 1. So, r 3 1 vector is 0.1 x cap minus y cap divided by magnitude of r 3 1 vector is square root of 0.1 x cap minus y cap into 0.1 dot product with 0.1 x cap minus y cap. Let me write it clearly here. R 3 1 unit vector is R 3 1 divided by magnitude of R 3 1, which is equal to 0.1 x cap minus y cap divided by magnitude of R 3 1 vector. So, let me calculate magnitude of R 3 1 vector. This is square root of 0.1 x cap minus y cap dot product with 0.1 x cap minus y cap. Square root. So, that is equal to 0.01 into 1 plus 1 which is equal to square root of 0.02, which is equal to square root of 2 times 0.1. So, R 3 1 unit vector is equal to 1 by square root of 2 x cap minus y cap. So, R 3 1 unit vector is actually along this direction and R 3 2 will be along this direction. So, it has both x and y components. So, I will leave it for you to calculate and show that R 3 2 unit vector is actually equal to 1 by root 2 into x cap plus y cap. Same magnitude, it is this is x cap minus y cap, this is x cap plus y cap. So, let me calculate the forces now. So, F 3 is equal to F 3 1 plus F 3 2, which is equal to 1 by 4 pi epsilon 0 q 1 q 3 by r 3 1 square r 3 1 cap plus 1 by 4 pi epsilon 0 q 2 q 3 by r 3 2 square r 3 2 cap. So, this is equal to now you see here that all the 3 charges in my problem are equal. I have taken q 1 and q 2 are equal as 10 nanocoulomb and q 3 is different. So, this is actually 1 by 4 pi epsilon 0 q 3 q 1 by r 3 1 square r 3 1 cap plus q 2 by r 3 2 square r 3 2 cap. Now, it so happens in my problem that q 1 and q 3 are equal. So, this is nothing but and not only that, the magnitude of r 3 1 is the same as the magnitude of r 3 2, because as you can see in the problem, this distance and this distance are equal because of the problem which I have taken. This is an isosceles triangle and these two distances are equal. So, what I get is essentially 1 by 4 pi epsilon 0 q 1 q 3 by r 3 1 square into r 3 1 unit vector plus r 3 2 unit vector, where I have replaced, I have assumed that r 3 2 is equal to r 3 1 and q 2 is equal to q 1. Now, what is r 3 1 cap plus r 3 2 cap? We have already calculated the two quantities. So, R 31 cap is 1 by root 2 x cap minus y cap, R 32 cap is equal to 1 by root 2 x cap plus y cap. So, R 31 cap plus R 32 cap is 2 by root 2 x cap. So, total force becomes 1 by 4 pi epsilon 0 q 1 q 3 divided by R 31 square into square root of 2 x cap. So, the force has only an x component, it has no y component, and let me substitute this. So, 9 into 10 to the power 9 into 10 nanocoulomb into 5 nanocoulomb divided by R 31 magnitude square. So, that was R 31 magnitude was 0.1 to square root of 2. So, that is 2 into 0.02 into square root of 2 x cap. So, we can calculate this and find out what is the net force acting on the charge, but as you can see from here, the problem has nice symmetry, because this charges are equal in magnitude, and so and the distances are equal from here. So, this particular charge, both are positive and this is also positive. So, this charge will be repelling this charge in this direction, this charge will be repelling in this direction with the same force magnitude, and their y components will cancel each other and their x components will add. And this was expected from symmetry of this problem, that the net force on q 3 should have been along x axis direction. So, you can substitute these numbers and calculate the total force, and I will leave the discussion here for the moment, and we will continue with discussion on more on superposition principle and its various applications in the next class.